All of them.
Okay, and we are ready to begin.
All right, very good. Okay, welcome everybody. Thank you for coming to today's talk. It's my pleasure to welcome Dr. Galen Reeves from Duke University. Dr. Reeves is actually affiliated with both. He has a joint appointment in electrical engineering as well as statistics, or statistical science they call it, a department at Duke University, where he joined not too long ago, in fall 2013. He completed his PhD from University of California, Berkeley in 2011, and then spent a couple of postdocs, one at Stanford with David Donoho, and one at EPFL in Switzerland. And he was also visiting the Technical University of Delft in the Netherlands, as well as the Microsoft Network Embedded Computing Research Group in the Seattle area, Washington. And he got his MS from Berkeley and his BS from Cornell in 2005. It's a pleasure to have him here to talk to us about some of his research on compressed sensing. So thank you for coming. The floor is yours.
All right. Thank you very much. So I guess the title of my talk is Robust Compressed Sensing. That's kind of the overall subject I want to talk to you about. But the subtitle is more about the tenor of the talk, which is I want to convey something about how undersampling distorts your data. If you have data and somehow you are only getting to see some subset of the information, you're going to have errors. You're going to have uncertainty. What can we say about the way this uncertainty is realized? It's going to be a very high-level talk. All right, I don't think there's any. There might be a few inequalities floating around. No equations, maybe a few equations, but nothing very long. All right. So to start out, kind of as we've been seeing more and more of, is that a lot of high-dimensional problems have some low-dimensional structure. And this is true across kind of broadly, I'd say converging across a number of fields, right? And how you want to think about it, from classical sampling, what can we learn from data, if you think of that as being the question of statistics. And machine learning, well, that's kind of always I think, right? You're just trying to draw a squiggly line between two different types of objects. But, kind of applications here, is medical imaging. What does high-dimensional mean, right? High-dimensional, somehow the resolution you want to attain, right? You want to know something about the density at locations inside of a human body, right? Low-dimensional structure is that, hopefully at least, the densities of tissues inside the human body just don't look like random noise. There's something, we have additional information about what we expect them to be. Data center monitoring. This is kind of another application where what's high-dimensional is you have these very expensive data centers that you need to run computing processes, and there's a lot of servers going on, and you want to tune them and try and say, oh, make sure that turn the right ones off, turn the right ones, make sure they're being energy efficient. Maybe if there's a crash, you want to know why did the crash occur. Somehow kind of just keeping track of all of these, they're generating, each server could be generating 100 performance counters every 15 seconds. It's a massive amount of data. To ask a simple question on it is very expensive. Right? So here you want to take some low-dimensional structures to even to ask questions about what's going on. Is there some way to look at this data? Again, I think it falls within this framework. Again, graphical models, low-rank matrix recovery. You're just throwing in some of the applications that can all follow here. And, kind of the number of applications grows and grows. And I think that, a lot of the times this can fall under the umbrella of things people refer to as big data. And I think, again...
Excuse me, North Carolina State, could you guys send us your PowerPoint? We're not seeing it. Ask your technician to do that. We're not sending the content. They'll know what I'm talking about.
Yeah.
Can we take it off?
We were, and now I'm going to have to get with Bob on that because it apparently went away.
Okay. All right. Thanks.
Can we take this offline, please? Thank you. Sorry. Big data.
You can go ahead. I'm going to work on this behind the scenes here.
Thank you. Please turn it off.
All right, so again, the overriding concept is what kind of, in these problems, right, n or p or whatever you want to think of signal dimensions very large, what's new, what's different, what can we say? And I want to think about signal estimation. Okay, from a concrete standpoint, think about we have some unknown quantity. I'm going to represent it as a vector here. Okay, the different values represent, you know, the unknown values of the entries. We observe it through some sensing system. Real world, there's always going to be some noise. We have our observations. And then we're going to do some processing on it to maybe try and get some estimate. Here we think about estimation. You might think about detection, classification, any type of recovery task. So what happens if somehow there's a mismatch? Right, kind of the number of measurements we see is less than the ambient dimension of the unknowns. Right, so here, if you think about it, a lot of unknowns, fewer observes. This is kind of, you know, one way to think of what's thought of as compressed sensing. More generally, compressed sensing any time that kind of the number of unknowns is more than the number of knowns. And can we do recovery? So compressed sensing became very popular, I think starting around 2004, 2005, well, at least under this name. And there's kind of three key components for saying compressed sensing says, yes, you can do recovery from fewer measurements. One thing you need is maybe your original signal should have to be sparse or compressible. That is, you know, there's some structure. This goes back to there's some structure to it, and you know something about the structure. So sparsity is a very popular form, saying that, you know, there's only a relatively small number of values in this vector which are large. Most of the others are insignificant. Okay, what's the second key component you need for compressed sensing? Incoherence. So the idea is that your sensing system must somehow be matched, or more specifically mismatched, with the compressibility of your signal in a way that you don't miss the important information. If you take a sparse signal and then just subsample it by just taking certain entries, chances are that you'll have a lot of the things you measure will be zero. A few will be the important components, but you'll have missed a large number of important components. So that's an example where your sensing system is not incoherent with the signal. Right? So you need some type of incoherence, especially saying that, you know, you're going to be spreading them out. You're not going to miss the important components in your signal. Okay, so sparse, compressible, incoherent. What's the third ingredient we need?
Low noise.
Low noise. Yeah, I think that's arguable. I mean, I'll say there's always noise, but we could say maybe it's really small. Maybe there's a lot of noise, but you just want a stable reconstruction. So that's a good point. But you need a recovery algorithm. And one of the keys, I think, steps that, you know, why was compressed sensing a theory that's been developed recently and not, you know, 100 or 200 years ago when Gauss and Laplace were doing least squares? And that's because, well, you need an algorithm. And, you know, for years what people have been doing are linear reconstruction. Okay? You can talk about its stability. It's computationally computable. Right? We could do it 200 years ago. Now we have computers. We can do much more complicated things. We can do computational reconstruction that's typically nonlinear. Turns out this is also going to be a key component needed in conjunction with the incoherence and the compressibility to fully get the benefits and to be able to work in this regime. Should also note, though, that nonlinear, from an analysis standpoint, is going to cause difficulties. It's much harder to say, right? As George was pointing out, noise is important. In a linear reconstruction, you know how noise is going to be amplified. It just depends on the size of your matrix, the condition number. In a nonlinear, a small change in noise could lead to very large changes in the outcome. That is, you could have instability. All right, so just kind of like put this into context. I think one of the big success stories for, you know, modern day compressed sensing is an MRI. Here the idea is, you know, it's unknown, maybe is what's going on inside your brain. Sensing system, you put someone in an MRI and you get measurements. Now, what you're actually observing is not the direct kind of physical space, but the K-space, as it's called, some transform of physical space. And so this, again, is an incoherent sensing system. And you want, at the end of the day, to get some estimate that hopefully looks like the brain. Is there an accurate representation for your purposes? You may say, well, what does it mean to assume that a signal is sparse or compressible, well, in this case, we might say, this image of the brain, it's not necessarily sparse in the standard domain, but in wavelets, maybe you can argue that if we do a transform on it, we know a priori that there'll be few significant coefficients in its wavelet domain. All right, so kind of the upshot here is what is compressed sensing giving us, right? Well, if you remember, the very first slide I had, I said in the sensing system, then I kind of burned away some measurements. What does that mean in the application of MRI? It means you can get away with fewer measurements and have the same kind of signal quality or reconstruction. Alternatively, you could say for the same number of measurements, you could get better reconstruction. Right? Why is this important? Well, MRI is a very, I'd say is probably one of the greatest success stories for compressed sensing, because this is a place where measurement time, the number requiring all these measurements, is a major factor in the cost, and also you have motion artifacts, and so it's an actual problem that compressed sensing helps. And kind of just to highlight this point, right? There's actual clinical studies where using compressed sensing techniques was able to improve the diagnostic ability of I think this was trying to do MR with children. And children are very difficult. They don't like to sit still for 30 minutes in an MR machine. Okay? So there's real science behind this, real results. But what I want to comment a bit on is, what's kind of been the driving force behind compressed sensing, or, what's the role of theory? And the fact is that people have been undersampling. And again, I'm using undersampling here to talk about getting away with fewer measurements and unknowns. People have been doing it in practice, especially from the 60s. In seismic exploration, people were seeing that if you include an L1 penalty, try and find a sparse solution, you got much better reconstructions. This was also done in astronomy in the 80s. And so, for a while, there were a number of people kind of doing compressed sensing. It wasn't called compressed sensing because the name wasn't there. And I think, maybe it's nice that people that got, some pushback. If they said, oh, I'm doing this algorithm, it works, and people would say, no, you're violating Nyquist. There's something fishy going on here, I don't trust you. Okay? So it was done in practice, but somehow not accepted in theory. Well, this kind of changed then with the increase of theoretical support, as people started to say, no, wait a minute, there's something more going on here. We can say theoretically that things are good and make sense. And so again, I just listed some things here. There's a huge number of paths, right? You can looking back that all kind of lead up to this. But the point I want to drive home is kind of that what happened with the papers of Candace and Tao and Romberg and Donoho around 2004 2005 was that all the theory came together with the three components. Right, sparsity, which had been in the literature, okay, that was combined with the incoherence conditions, theoretical conditions, and finally an algorithm. Right, in this case, an efficient actual algorithm that works. All three together kind of then said theory says, oh, now we can do this. And so, again, here's a slide just talking about the impact. So this is citations of compressed sensing, and you could argue, okay, maybe it's a little fishy. Why would there be any mentions of compressed sensing before it came out as a topic? But what I really want to think about is kind of how the theory's taken off. And theory kind of has allowed people to do this in practice. So, where are all the new applications of compressed sensing? Well, just think about all the places now where people have been doing it that it's now legitimate. And again, I also included on this list, right, so not just the Google Scholar citations, but kind of PubMed, just showing that these scales are different, so it's an order of magnitude different, but you have a similar kind of a rapid increase, right, in the amount of content. All right, so let me introduce kind of a basic model of compressed sensing, be a bit more specific. We'll call this the k-sparse model of compressed sensing. Here we're going to think about exactly a sparse vector, x, and it has maybe k non-zero locations. We think about, to observe this, it's going to go through, the sensing system here will be a matrix. We're going to think of it as an m by n matrix, m less than n, added to noise, and here's what we observed. So I've arranged it pictorially. So if we have this expression, right, a vector, it's multiplied by a matrix to get a smaller vector. There's some noise. What is this? Right. In linear algebra, we think of this as it's just a noisy and underdetermined system of linear equations. Right? If we didn't have any noise, it's just an underdetermined system of linear equations with the noise. So the question is how can we solve, how should we go about reconstructing x from y? All right. So the basic question, how many measurements do I need for the k-sparse model? A k-sparse vector, length n, how many measurements m do I need? This is,
With noise or without noise?
okay, let's say without any noise.
K plus 1.
K plus 1. But it's a length n vector, sure. Saying n doesn't matter.
Yeah, it's K sparse.
Well, you're absolutely right. Okay? It turns out if there's no noise, all you need is k plus 1 measurements. This is just a fact of, okay, I should say maybe random measurements. Supposed to hold almost surely. You might have heard, sometimes 2k. This is the difference between, guarantees which hold, for any x with probability 1 over some random measurement matrix or universally simultaneously for all vectors. But that aside, right, k plus 1 is the answer. Everything else in compressed sensing must be, all these other papers must be addressing some different question than how many samples do you need for a k-sparse vector and no noise. Okay, well, there's two problems. I put them here. First, computational issues. In order to find this, it's an NP-hard problem. You have to kind of go through all possible subsets of size k and find the one which looks the best. Right? There's n choose k such subsets. It's not, it doesn't appear to be computationally easy to do this problem.
Galen?
Yeah.
Excuse me, I hate to interrupt. I think what happened there, why we lost that, is because when you switched over to mirroring.
All right.
So what I'm wondering is, because we're supposed to be displaying at 1024 by 768 resolution, and I'm wondering if your resolution settings messed with their ability to see the content. And I really hate to interrupt you, but I think that's what caused it.
Well, does this fix it? I just put it on
Okay.
mirroring.
Okay. Let me try that again. Go ahead and continue, and we'll keep working on it just to make sure.
Remote sensing is more difficult than compressed sensing. Okay. So in the hundreds, not thousands of papers, right, we're addressing these issues. Computational complexity, stability with respect to noise, and also, of course, come on, is anything really k-sparse? Well, in some cases, yes, but in a lot of cases, no. Okay, so, all right. So this is just, this is just a subsample of some of the literature, bounds, right? So now you want to do compressed sensing, okay? You don't want to run an NP-hard recovery algorithm, so you're going to use some convex method, and so maybe you want to look and say, hey, maybe I want something with complexity that's polynomial. And so you go into the literature, say you want to do reconstruction. You open up a paper, it promises you reconstruction bounds, and you find, okay, how many measurements do I need? And your answers are, okay, well, in some cases, you have this k plus 1, k squared. These are kind of these special cases and no noise. However, once you go into kind of saying, all right, I want efficient algorithms, I'm going to start getting these order results. And in fact, now when we look in noise, right, we're having this big O, big omega. So big O says there's some, it's an asymptotic, it's an upper bound, right? So there's some constant C, such that the expression for all kind of parameters, right? As you think about growing the system, it's going to increase scaling, right, by some constant. I'm not telling you what that constant is. And again, with this omega, it's some asymptotic lower bound, right? Again, as these parameters scale, right, your signal gets large, the number of non-zeros gets large, the number of measurements get large. It says something about how they scale together in terms of some unmentioned constant. Okay, this is great for theory, but hard for the practitioner, right? When you have a problem, where does it sit on these order results? How do you translate the order results into a single instance, right? You have some fraction of measurements, right? That's a number. You have some, if you have sparsity, it's some fraction of coefficients are non-zero. These are numbers between 0 and 1. Right? So I think that, this shows that the theory works, but how do you use it in an engineering sense? Yeah.
So when you say linear sparsity, you mean like a fraction of the original?
Right. So again, again, I'm just showing a subset of the conditions, somehow to minimize the number of equations. But a lot of these times these conditions say, if your sparsity, the fraction of non-zeros scales, like something with n. So it's like, say your fraction of non-zeros is on the order of log n, right, then the ratio of non-zeros is going to 0 at some rate, and then you get away with so many measurements. Okay. Or as the noise is growing at some rate. So that's how it works. So what I want to know, though, is, what can you actually do? What are the trade-offs? Right? If you want to use compressed sensing and you say, okay, I'm going to try and use half as many measurements because it's going to save me money here, does that mean that your mean squared error is going to increase by a factor of 2, or a factor of 200, or a factor of 2 million? All right. So at this point now, I'm going to, there's a lot of questions one could answer here. But what I'm going to try and do is give you guys a feel for a certain aspect of what's going on from undersampling. As I'm going to say, right, as I said, undersampling is doing something. It's you're losing information, and you can think of this as adding noise. So I'm going to say, how does it add noise? And then secondly, what can we do about it? All right, so let's start with a motivating example, where I'm going to ask if you guys want to do some compressed sensing here. What I have is I took a 512 by 512 image, okay, pixels. I stacked it into a single vector. So this is my unknown vector now, is n, where n is 512 times 512. Very large vector, and that's this gray vector. I made it gray because I don't want you guys to see it. It's unknown. Now I'm going to take measurements of this with a matrix. And my matrix is going to have exactly, the number of rows will be half the number of columns. So I'm throwing away half the components. And that's this green matrix. But if you look at the matrix closely, you'll see that actually it's got lots of dots, right? This is the matrix I used. Okay? I'm showing you the matrix. The intensity of each pixel in that matrix corresponds to the value in the actual sensing matrix I used. So what you have here as our measurements are a multiplication of the vector with the matrix. Okay? It was hard for me to figure out how to show you the measurements, so what I showed is these are actually the measurements I got. I showed them here kind of as a plot. Okay? So what you see is you know the measurements, you know the left-hand side of the equation, you know the matrix. These are the unknowns, right? There's no noise. So my question to you now is, what is x? Right? I'm showing you everything. Okay? You just have to do some computation. Okay? Now, any guesses? Okay, you may argue I didn't give you the scale here, but that doesn't matter, right? Because it should just be then proportional to whatever's here. Else I didn't give you the scale here. So I did give you enough information. Your complaint might be is that it's a bit computationally nasty to sit here in the audience and try and do some inversion mentally. What I'm going to propose is saying, well, what if we just do a very simple procedure? Forget about compressed sensing. Is this a sparse vector? I don't know. I didn't tell you it was sparse or not sparse. So why do compressed sensing? What can we do for recovery?
You could brute force it. You could guess and check, brute force it.
So one option is guess and check. That is, pick a vector here, see if it then gives you the measurements. Okay. Well, this is a large vector. Okay, this might take a while, right? You could go through. So that's one way, kind of like some ML. And we also know that since this is underdetermined, right, there'll be a whole, there's an infinite number of solutions to this system of linear equations. I'm asking you to choose one.
Choose a pseudo-inverse.
What was this?
Pseudo-inverse.
So one suggestion is to take the pseudo-inverse. Now, there's different pseudo-inverses. I think there's the standard Moore-Penrose pseudo-inverse you can define in terms of rotating and then inverting the non-zero singular values. We could also think of other generalized linear inverses. And so what I'm going to do is just this. I'm just going to take a linear inverse. Instead of using kind of the Moore-Penrose, I'm just going to use the transpose of the matrix. So I'm just going to take my measurements, hit them with the transpose of my measurement matrix, and see what I get. Do we think this should work? Well, it's L2, right? We've been told L2 is bad and all this. Well, let's see what it looks like.
The problem is the content.
But do we see something? Right? So without doing anything else, just taking the transpose of the matrix and hitting it, I don't know, people are laughing when they see what we see. You know something now about this unknown signal. Do you think this is the solution? Do you think this is the original picture? No. But it looks like a very, very noisy version of a picture of a person. Okay? And we can see this kind of coming through the noise. So what's something we might do at this point? We have kind of ideas going off in our heads. We're saying, the unknown signal was a natural image, picture of a person. What do we know about natural images? Are they compressible?
They're sparse in BCTs.
They're sparse. Well, they're usually pretty sparse in some wavelet domain. Okay? So now that we think this looks like a really noisy version of a natural image, we know natural images are sparse in a wavelet domain. Let's transform it to the wavelet domain and threshold it. We'll try and do denoising. So we're going to do wavelet denoising. Oh yeah, but first I want to show you guys. Here's the histogram. Before we do any of this, this is the histogram of the errors. So I'm giving you some more information, okay? I still withhold the true picture. But if I compute the difference, pixel by pixel, between that estimate I just showed you and the true one, this is the histogram. Okay? It looks very normal. Okay? So those errors we saw just by hitting with the transpose, somehow it looks like at least the marginal distribution of the errors on each entry is normal. And zero mean. Okay, here's some more information I'm giving you. This is the histogram of that original unknown signal that I didn't show you yet. And these are the values. So I've subtracted it from 0. The centering doesn't matter. It's from 256 scale are the values, right? And so these are kind of the dark intensities. These are the light intensities on an image. And you see that it has this profile. Okay? This, however, is the histogram of the estimate I just computed. So the original definitely has some behavior going on, right? The estimate, though, looks like a big blob. So I don't know much yet. Maybe this is consistent with taking this original histogram and convolving it with a very fat normal. Okay? Maybe it is, maybe it's not. I can't make that argument yet. This is more information. In any event, we're going to assume, right, we have a natural image. Let's do just what I said, wavelet denoising. So I just denote it here as we take our estimate from before, we transform it into a wavelet domain. We apply some threshold. So here's the self-thresholding function, which just, everything below a threshold gets set to 0. Everything else gets shrunk to 0. And, by the way, we could do other thresholds. We could do any number of denoising operations here. Self-thresholding is nice because it has got a good theoretical properties that make it robust in some senses. We'll see later. Okay. And then we transform it back. Okay, so I'm going to do. I haven't done this. This is the linear estimate, and now I'm going to denoise it. So it's changed a bit. It's gotten a bit smoother. Right? I don't know if you can see, but that there's the blocks right. It doesn't have quite all that noise as before. But it's not clear this is a better image to look at. Okay. So what are we going to do? Well, I have an estimate. One thing we could do is say, let's kind of take our current estimate and try and update it iteratively. That is, this is our current estimate. Let's estimate it from our measurements, the effect it would have. Let's use our previous, again, use it, and then add back in kind of applying a linear inverse, our same crummy, just A transpose on the residuals.
It's Van Sittert. Is that Van Sittert?
Maybe. What's this?
Okay.
Yeah. So this is nothing new. This is an algorithm that's probably been done many times. It's kind of it's known as, in this case, iterative self-thresholding. But what I'm going to show you again is actually you can do variations on this a bit more advanced. So I'm not going into the details. The idea is what we're going to do is we're going to alternate between two steps. Doing a linear inverse, denoising. Taking our estimate, updating our best, now then trying to compute the best new linear estimate based on subtracting out our current denoised version and repeating. Okay? What I'm going to show you is not actually just the simple step. I'm going to use something called approximate message passing where there's an additional correction term. Okay, to try and keep things going more stably. And let's see what happens. Okay, so now what I've done is this is the second step. I've taken my linear estimate, denoised it, and then created my new linear estimate. Does it look better? No, it looks worse. Okay, well, let's just go ahead with this. So I'm going to do now, there's a process, back and forth, many times, and we'll see what happens. So here's again. It's time to look better, a bit better, a bit better. Okay, I'm going to keep going. I think I do about 20 iterations. And we're starting to see maybe we even know who this person is. Okay. Done. Put that up there so I knew when I was done. Okay. The algorithm's converged. Our iterations aren't changing anymore. This is our new picture. Okay. So starting from knowing nothing, just kind of doing the transpose, looking at it and reasoning about what we saw, right? We were then able to use a better algorithm, right? We said, oh, let's do self-thresholding in wavelet domain. Doing that many times, we reached what appears to be a pretty good construction of what we, I'd say, reasonably think I used as the image. What I want to do now is let's look at what I've gone ahead and calculated. I know ground truth. I'm going to calculate the distribution of errors at every stage in those iterations, okay? So this was our distribution of errors at the very first iteration. What happens if we went through those iterations? Okay. At every stage, the distribution of the errors is normal. This is the marginal distribution. And in fact, as we do more and more iterations, all that's changing is the width of our normal is shrinking. That is, we are getting an image that looks as though it's been corrupted by additive Gaussian white noise, IID Gaussian components, but the power, the noise power, is decreasing with each iteration. Okay? And this is true from the marginals, right? I'm not doing any theory here. This is just an experiment, and I'm showing you what it looks like. Let's do a similar experiment. This time, let's look at the difference between the distribution of the entries in our true signal and the distribution, the histogram of the entries in our estimate. Okay, I'm going to go through the iterations again and see what's happening here. Okay, so it starts out, right, we had something that was very blobby. But as I get more and more measurements, what we're starting to see is that the histogram of our estimate is converging to the true histogram of the data. Moreover, if you look at the difference here, what's happened is as though you took the two distribution and you convolved it with a Gaussian of a given width. Our Gaussians are getting narrower, so as you convolve it with this Gaussian, the smoothing is less and less, and we're getting a better look at the distribution. Okay? So there's something else that's remarkable which is going on here, right? One pass, we got information about what it looked like. Now, by the end, we also have a very good kind of look at exactly what the distribution of our underlying signal was. So what's kind of making all of this work? And that's this fact which we just observed kind of, I would say, experimentally, which is that somehow our undersampled system, right, which is what I started with, just taking half as many measurements, is behaving very, very, very much like a system where we had direct observation. That is, we had a full number of measurements, but we had it on Gaussian noise, where the components of the noise were independent of the components in our vector. And what was that effective noise? Well, the effective noise changed. When I just did a simple linear inverse, the effective noise was very large. But as I did better and better reconstruction, I went further and further down the line, my effective noise was becoming smaller and smaller and smaller. So somehow, that effective noise is a function of my decoding algorithm, my recovery algorithm. And it's also a function somehow of, well, if there was any original noise in the problem, it'd depend on that. It's a function of the amount of undersampling I have done. Okay, more undersampling, there's going to be my effective noise will be larger. It's a more difficult problem. And it's also a function of, again, of the distribution of x itself. Okay? So here's a plot I made of the standard deviation of the noise as a function of iterations. And we see that as our iterations went along, it decreased until it hit to some level. It stopped here. It leveled out at a value of about 12. Okay, so the image I show you at the end, though it looked good, it was still noisy. Right? It still had a width of about 12. Why did it hit bottom out here? Right? Was it because I was using a bad algorithm? Was it because I was using soft thresholding? If I'd used a better denoiser, could I get it lower? Is it because drawer is not actually sparse? Oh, sorry, that picture was of drawer, I should say. I think it's obvious by now. Okay. So I've just shown you something, right? And you might think I made up these photos, you know, these examples, right? So if you want, there's theorems that describe everything I just showed you. Say it explicitly. In the terms of they're typically stated. Okay, for these theorems, you need the matrices to be IID and random, so that kind of these matrices are generic. So it's depending on it's the randomness in the matrix. And you need kind of the signal dimensions to be large. But then the statement is that this idea that undersampling is just like adding Gaussian noise is again, true. And precisely true. And for a number of cases. Here I just listed a few. One is if you're doing Bayes estimation with respect to, say, think X is drawn, the entries in X are drawn ID according to some distribution. Okay? If you do Bayes estimation with respect to that distribution, the statement's true. Now imagine that you do Bayes estimation with respect to a wrong distribution, a postulated distribution. It's still true. You just have a different effective noise level. Imagine you want to do something like a map estimate, or ML. The statement's still true. You just have a different effective noise level. Say you do approximate message passing. The algorithm that I just showed you before. It's true. You might have a different effective noise level. Right? Or you can do AMP with spatially coupled matrices, specially designed matrices, and you get true. So in all these cases, it's true that your noise, the effects of undersampling are like adding Gaussian noise. The question is how much noise? And I think the right question to ask when you're looking at compressed sensing is not to say, does my matrix satisfy the restricted isometry constant? Is my scaling of my constants on this order, this scaling regime? But is what's the magnitude of the effective noise inherent from my undersampling, and how do I reduce it to make it as small as possible? And again, we see the effective noise as a function of the undersampling, the recovery method. These 4 different kind of recovery methods, sometimes they'll give you the exact same amount of effective noise. Sometimes one can give you an effective noise that's very small. You get almost exact recovery, while others have an effective noise that's very far, that just blows up. Right? And so the difference in effective noise is why compressed sensing, kind of like using L1 works, but without L1 fails. Okay, when you use L2 methods, you get a compressed sense, you get an effective noise, it's very large. Using the L1, you can greatly shrink it. And also the amount of measurement error. So one point I'm not going to touch on here is that for a broad class of recovery tasks, all that dictates how well you do, whether you're trying to do detection, classification, regression, it's the size of the noise power that matters. And I think this is also related to the work that Dror's been doing here, right, with kind of how the noise power tells you about the effective, the performance you'll get for a variety of recovery tasks. Okay, so I'm going to give you a specific example now. So before, in this case, right, I'm just telling you that it's true. And then I'm telling you the right question is say how much noise is added. So it turns out you can be very explicit about how much noise is added. I'm going to show you 2 cases, one for Bayes estimators and one for AMP estimators. What are the ingredients? What do we need to do to calculate the effective noise? First, we need our undersampling rate. So that's what this term is, delta, number between 0 and 1. Just a fraction of unknowns to knowns. Knowns to unknowns, sorry. What else do we need? We need some initial measurement error. Here it's normalized to 1, so I think you could just plug in whatever initial measurement error you have there, the size of your measurement error. What else do we need? We need the empirical distribution of the entries in our vector x. So that was that when I showed you those 2 histograms, that was the top histogram of the drawer image. Okay, that's a distribution on a real valued random variable. It's a distribution. Okay, so we're going to encapsulate that in a random variable that has that distribution. Using these 3 kind of quantities, initial noise, undersampling, distribution of components, we can now define a functional. Okay, this is called the Gibbs free energy, but the important thing is that this functional depends on this parameter tau. This parameter tau is the stand-in for your effective noise power. So the x-axis here is you kind of saying, let me, postulate, would I get this effective noise power? Would I get this effective noise power? And then you're going to evaluate this functional. Okay, and so across the x-axis, what you'd like is, you like noise powers that are over here to the right, that are small. Small noise power, accurate recovery. Large noise power is bad. So it turns out for 2 kind of algorithms, so I'm going to call Bayes. Here kind of Bayes by mean optimal. You know the distribution on x in advance and you're doing the optimal thing. AMP, I'm going to think of this as an optimized AMP. We're using a Bayesian version of AMP. Specifically, when you do the denoising step, you're doing it using a Bayesian denoiser, but you're still running this iterative algorithm. Okay? Well, it turns out that this function is going to tell you explicitly the noise you expect to see. For AMP, you're going to look at this function and find the minimum. Okay? You're always guaranteed this thing's going to have a minimum. It blows up as the effective noise goes to 0 or infinity. So there'll be a minimum. You find the location of that minimum. Where it hits the x-axis, that is your effective noise power that you will see in this system. Okay? For Bayes, similar thing. You're going to have a minimum. You find the minimum of this function. That is your effective noise power. So in this case, there's only one minimum. I think that's true. Well, it could be seen. It's kind of hard to tell there if it flattens out. But what's important is that AMP says the largest minimum. So you find any local minimum, choose the one furthest to the right. That's what AMP guarantees you. Whereas Bayes says find the global minimum. That's what you get. Okay, so I haven't told you where these expressions come from. And they come from two wildly different processes. Okay, to derive this expression for Bayes, this approach built from statistical mechanics, where it's based on the replica method, and you're trying to analyze the system and its typical behavior with respect to random matrices. Whereas the analysis for AMP actually comes from analyzing the algorithm, whose performance I just showed you, and tracking it at each iteration and seeing how the noise decreases until it hits a fixed point. That fixed point corresponds exactly to a critical point of this functional. All right, so in this case, one minimum, they're the same. What does this mean? Using AMP, you get the same noise as if you did Bayes. That means AMP is as good as Bayes. You can compute the Bayes estimates. You can do the optimal behavior for this distribution using AMP. And by the way, I should mention, AMP, lightning fast. Very, very computationally efficient. Okay. What happens, though? Remember I was saying the effective noise depends on the undersampling, so I'm keeping that fixed. What happens if I just start changing the distribution on X, though? Right? The effective noise also depends on how difficult your signal is to estimate, kind of if you just had direct observations. So I'm going to change the distribution and look at some different curves here. Okay. Well, here it is for a different distribution. Different distribution. Different distribution. And we see what's happened. Is as I've changed this distribution, in fact, I can tell you what I'm doing with this distribution. I'm actually just taking the distribution and increasing its power. All right, so if you want to think about it, kind of the effective power of my, if the components used to be small, now they're all a bit bigger. What's happening is that the largest local minima is getting larger and larger. Okay? So if you're using AMP, and I start heading in this direction, and I keep doing this change I'm making to my random variable, what you're going to see is your mean squared error is going to keep increasing. The blue dots keep going to the right. Okay? And in fact, this is in a regime where approximate message passing is not stable. Right? So it's outside of the recovery phase transition regime of approximate message passing. You can keep doing this, and your approximation error would be unbounded. Okay? So kind of this is something where out here, AMP no longer works. But if we're able to compute the Bayes rule, right? Now this one could be computationally, in principle, at Bayes, you're taking the expectation with respect to the conditional distribution, the posterior distribution. It could be numerically, to write down the integral, right? It's not, you don't want to solve it directly. So here, we're being able to solve it efficiently, but here, it's somehow saying if you could solve it, it's promising you a very good noise. Very good, I mean small. You're getting very accurate reconstruction. So in fact, as you increase in this direction, the optimal recovery algorithm is doing better and better and better, whereas AMP is doing worse and worse and worse. Whereas here, they're exactly the same. And this change is the discontinuity when this new minimum became the global minimum. Okay, so a very small change here in the parameters can make the difference between knowing almost everything, so using an efficient algorithm, and knowing almost nothing using AMP. Yeah?
So you say low power in the signal is better for AMP in some sense?
Right, so here's a trade-off, and I'm not going to go into too much detail, but part of the question is which is more difficult? To estimate a signal, so I'm going to evaluate you on your mean squared error. Which is more difficult? Is if your unknown signal has very small values or very large values? Well, if the values are very small and there's noise, okay, you're never going to see them. They're lost in the noise. So in some sense, you're sad, right? I can't see my signal. But on the other hand, well, just guess 0. Your mean squared error is small. I said your signal's small, your mean squared error is small. So you're happy. Now, what if the signals are very large? The components are very large, okay? If you make any mistake in estimating them, it's going to hit you. It's going to really hurt you, right? If your non-zero components on the order of 10 to the 8th, right, and you're off by a little bit, well, your fluctuations could be on 10 to the 5th or 6th, right? You have very large mean squared error. But if they're very large, then that noise is effectively very small. So it's like you have hardly any relative. Your SNR is very good, and now you can see the components. In fact, if it's sparse, you can actually identify. The one way what you see is that what happens is it becomes this trade-off where you're suddenly able to detect the locations of all the really large components. And that detection probability, error probability goes to 0. You're able to find them. You can do regression onto them without any error. So in fact, the worst spot's somewhere in between, where you're right on that critical boundary of not quite being able to determine which components are large, which ones are 0. And yet when you go and try and do reconstruction, the errors are still on the same magnitude as your signal. And that, again, is why looking at it, you set up the problem correctly such that the limits aren't somehow in the 0 noise or the infinite noise case, but right in the middle where everything's most contentious. OK, so this was... Oh, yeah.
If you want to interpret it that way, so if SNR is not very high, then you don't have much information. In that case, you're saying if you don't have much information, you don't have to do much processing. Is that?
I guess a better way of saying it is I'm just penalizing you on your absolute mean squared error. If you wanted the mean squared error divided by the magnitude of x squared, then it will always be very difficult in the limit of small noise. It becomes different. So it's more a question of how I'm thinking about mean squared error. OK, so this was an example, right? I showed you first an example of what noise looks like, effective noise. Now I've showed you that you can actually analyze it and get precise expressions for how it behaves and think about these. All right, so this brings me to the second part of my talk. So again, just to recap, right? I said undersampling is like Gaussian noise, like adding Gaussian noise. And it's not that you're adding Gaussian noise. It's through the effect of the algorithm. When you do the reconstruction, your estimates look the same. And I said, again, the noise, we now know the noise to power depends on these various properties of our problem. What can we do about it? And now I'm going to overview and kind of just highlight some of the research I've been doing in this area and how it fits in and how it's, I think, hopefully to answer, right, we want that effective noise as small as possible. So first thing is we can think about robust estimation. This is kind of a game against nature. We can think about some class of signals or distributions on signals, if you want, right? These could be all k-sparse distributions. I mean, all k-sparse signals are all distributions that would result in a k-sparse signal. It need not be k-sparse. You can think about any general class. You can think about some class of recovery algorithms, right? This could be, you use lasso, and then you just have to choose the tuning parameter. Or it could be you use AMP, and you have to choose the nonlinearity in the tuning parameter. Or it could be the denoising tool. Or it could be that you just have the class of all possible recovery algorithms, right? You can use anything. And somehow, in this problem, right, there's two trade-offs, right? You think of nature is out to get you. Nature wants to choose a distribution, x, that's unknown to you, that makes the mean squared error as large as possible. Okay, well, statistician or engineer or scientist, right, practitioner, you want to choose an estimator that's good. And of course, there's two options. If nature plays first, on the left, right, that is, nature commits first to a signal, or in this case, you think of it as a distribution over signals. Okay, if you knew the signal, right, you just output it. So you might think now in this case, nature's picking a random signal in the class, and you have to pick an estimator. Well, you do Bayes' rule, right? There, the optimal behavior is conditioned by the conditional expectations. And so the worst case of all signals in a class is kind of the worst case Bayes in that class. The other hand, what we're really looking at is the minimax risk. Okay. So we pick any estimator, and it's going to get evaluated on the worst case signal in that class. We want to minimize. We want to find the estimator that has the best worst case MSE. And there's a relationship between these two, which always holds, right? I said not too many equations, but some inequalities. Is that the minimax MSE, right? This is a more difficult game for us. So it's going to be larger. What's interesting, though, is we can ask several interesting questions here. One, for a given class, say sparse signals, what is the worst case distribution in the class of all sparse signals? Why is this interesting? Because this has the interpretation of the most difficult prior for compressed sensing. Moreover, if you want to do simulations, and you're going to show me how well your algorithm works, it'd be nice to show how well it works on the most difficult distribution for compressed sensing, not just one you chose, which maybe it just happens to work well for. For here, the interpretation of this, in some sense, if all you know is that your signal belongs to a given class, you have no additional information, then why would you use something this? If you could say what the optimal thing to do is, then that's what you should be doing. So in the robust sense, this is the optimal behavior. Moreover, is this inequality an equality? So you kind of have a minimax theorem where you can say you can swap the order of the min and the max. Maybe we have a saddle point where our strategies don't change. And that's interesting. Right? It's interesting for a few reasons. First off, if it holds, it's very nice, because it means that just doing the Bayes rule for the worst case prior in our distribution is minimax over the whole class. And it also means that somehow the order of the game doesn't matter too much. It's also interesting if it doesn't hold with strict inequality. So there's a lot more that could be said here. I'm just going to touch on some certain cases and maybe leave some open question, which is, do you believe intrinsically there should be equality here or inequality? We'll see. All right. So the first example I want to talk about is say, we need not believe things are sparse. In fact, why in the case where I was trying to reconstruct drawer was there still noise? Why did that system bottom out? If you look at the phase transitions for A and P, which you can get by analyzing that whole effective energy plot I showed you, you will find that we were actually taking half the measurements isn't bad, and if drawer was reasonably sparse, say if drawer were 20% sparse in, or I think 19% sparse in the wavelet domain, we would have had exact recovery. But we didn't have exact recovery, and it's because drawer is not 90% sparse in the wavelet domain. All right, there's more to him. And so, again, we had some deviation from strict sparsity. Now, maybe there was some domain in which drawer is more sparse, right? There obviously is one, right? If we had a basis that had drawer, the image of drawer as column 1, right, then he's one sparse in that. The key is we have to pick our basis ahead of time.
Right? It's called the URL of my web page.
This is the basis for your one sparse. Okay. It's, and so again, can we characterize? So one way to say it is say, let's imagine that our signal. So first we're going to say consider all signals that are close. And that is, we say we're close to being k-sparse, such that you take the best k-sparse representation, and then the difference between that and the true vector lives maybe in some LP ball of a given radius. So LP, right, I'm just taking to the pth power. P can be between anything greater than 0. Right? So you can have P, less than 1. These are very interesting. These are kind of like weak sparsity balls. Or you can have P larger, right? P equals infinity just means that the maximum deviation away from k-sparsity is bounded. Okay? This is a class of signals. And what we can do is then we can look at maybe a class of algorithms. Maybe I'm going to do A and P with soft thresholding. So the question is, how do I choose that threshold? Remember, if I showed you the soft thresholding thing, I had a question, threshold. And it turns out that here we show there actually is a Minimax theorem. The optimal threshold, so kind of if you fix a threshold ahead of time, and then nature chooses the worst distribution, it's the same as if nature chooses the worst distribution and you choose the best threshold for that. They're the same. There's a saddle point. Moreover, we can tell you exactly what that worst case mean squared error will be evaluated at that saddle point. And these are some contour lines here where we're just doing it. I mean, obviously, these worst case depends on the degree of undersampling and the sparsity, your radius. So I'm just plotting it here as kind of your initial, if you have additive noise on your measurements. And on the x-axis depends on kind of the radius. This is for a fixed p. I think this is maybe an LP ball with p equals 1. Okay, so you can compute these things for any parameter you want. You get out the numbers.
So how sensitive are these to the deviation of your Gaussian assumption? Suppose you have a mixture noise now.
Mixture noise for,
like say, partially spiked noise, partially Gaussian.
Okay, so there's two things. What am I making assumption about? I'll tell you. The key assumption I'm making is about the matrix. I'm not really assuming anything about if I have additive measurement error. As long as my matrix has enough randomness in it, it doesn't matter what my measurement error is, because when I hit it with the matrix, it's going to look like random noise. There'll be incoherence between my measurement error and my matrix. So I'm not going to assume much about the matrix measurement error except that it doesn't depend on my matrix. For my matrix, what I really need is something like IID. IID is too strong, close to IID. IID Gaussian works for all the theory. IID works for some of the theory. And there's a big push to see how much you can reduce that. Now, as you go away from kind of columns that have interchangeable columns or rows, then you're going to add more additional assumptions onto something about the measurement error and the noise. Really? So Gaussianity of the effective noise is coming out of a law of large, or a central limit theorem induced by the incoherence of my matrix. It's not coming from an a priori assumption of Gaussian noise, measurement error, or necessarily the coefficients of the matrix themselves are Gaussian.
But it will impact your MSE, right?
It will. Well, to answer that question, right, the right way to do it is to say we have all these predictions, test them. And in fact, there's this nice paper David Donoho did with his compressed sensing class at Stanford, where he says, here's a bunch of phase transitions. Everyone take a matrix construction. Here's all these different matrices and test it. Run, thousands and thousands of CPU cycles, get the phase transitions. And let's get confidence intervals, just like you have a hypothesis that this matrix will have this phase transition. You can test the hypothesis. And it turns out that for a large number of even certain well-designed deterministic matrix instructions have the exact same empirical phase transition. So it's giving you a really testable hypothesis to see about where you think things will happen, and also how to tune things a priori. But your point's well taken, right? I'm not quantifying how these things change due to changes in the matrix.
So, from what you just said, it is implied that the restricted isometry property is less important than as stated by some others, right?
Right. So what's going on here is I'm not asking at all if the restricted isometry property holds. And in fact, I can prove in many cases that you can be stable. You can have stable recovery in cases where you know for a fact the restricted isometry property does not hold. There are very bad, ill-conditioned subsets. They're just not typical. Typical behavior is way better than the worst case behavior. And so if you're just stuck looking at restricted isometry, you're going to get bounds that only allow you, in some cases, right? You can say, oh, you can, get away with undersampling by a minuscule fraction. Very pessimistic between what you actually get in practice. Now, if you want deterministic bounds that hold uniformly over sling, okay, maybe if in that application, then that's where sling with the restricted isometry theory is more applicable. But I'm talking about what I consider the typical behavior. So maybe another example, right? If this was a nice class of distributions. Maybe I'm looking at AMP. Again, we can look at the class of all possible distributions. No more constraints on computational complexity. And here I'm going to constrain my class, all k-sparse signals. And here again now I can get fundamental upper and lower bounds on the minimax sensitivity to noise. So what I'm showing here, and so I put approximately, because my upper and lower bounds are finite in the same region, infinite in the same region, and not too far apart in between. Well, far apart's relative, but so it's approximate. So again, the point here is this is the ratio. This is the worst case ratio if I kind of divide by the noise power and says how much does adding noise hurt me? So measurement error on the outside. And it says that it will hurt you by at most a constant factor here. This is that constant. If your degree of undersampling is small but not too small, if you become too small, the effects of additive noise are unbounded. And the phase transition here occurs right at that noiseless limit we talked about at the very beginning, k plus 1. In the absence of any noise, you need k plus 1 measurements to recover. In the presence of noise, you need greater than k plus 1. Actually, it's kind of interesting. In the theory, you see k plus 2 measurements for your expected mean squared error to be finite relative to your noise. So again, it's coinciding to the fundamental limits. It makes it there's no gap. If you do RIP theory here, you're going to see an area. You're going to see this curve. I can plot the same curve, but it's up here. Is that a question or 3 minutes?
3 minutes.
And it's not a question. Okay. Well, that's good because I think I only have a few more slides. Okay. So, and maybe some more kind of general results, right? Is we can grow our class of possible estimators. So here I'm going to keep class of all possible estimators. So really saying what is the fundamental limit, right? Oh, and by the way, I just wanted to mention that here there's upper bounds and also lower bounds, and lower bounds are qualitatively similar. Here, so this is a class of all possible estimators. I'm going to look at a very broad class of signals. Basically, anything that's close to a given finite dimensional, finite union of affine subspaces. Okay, so this is a union of subspace models. This isn't new, but I can show it's very powerful in what I can do with it. And I may just say this in words. But again, I show that the fundamental limits for recovery, right? If you use RIP theory, if you use all these deterministic conditions in the literature, it says you can do a union of subspaces, but you need, in order for stability, you need the measurements to be greater than order k log n over k, where k is kind of the size of dimension, or here d. Here, I'm proving actually no. All you need for stability is the number of measurements must exceed the dimension. It could have a very large constant, but this constant is finite, and as you get more and more measurements, it will decay. You will get better stability. So again, using these tools, I'm saying where the actual phase transition occurs as opposed to kind of very loose sufficient conditions. Oh, it's like bugs. Okay. So maybe one last part, and I'll just say it briefly, is we also saw this other added benefit. When we know the statistical distribution of our errors, and not only that, the joint distribution between our errors and our signal, we know that our errors are like independent Gaussian noise. We know that the observed histogram is going to look like our true histogram convolved with noise, with a Gaussian kernel. Sure. And so can we learn the signal, right? One idea is, well, maybe we just deconvolve, right? And then we could see our estimate, and then we can do Bayes, right? And so maybe if you start saying, well, if I can deconvolve from my empirical observations to here, I can do the Bayes estimate. Whoa, remember that min-max, max-min thing I showed you before? They must be equal, right? Not quite, right? It's not trivial to try and do deconvolution. I mean, this is a discrete distribution, the empirical, but you actually know that after you've convolved with the Gaussian kernel, right, in reality, it'd be smooth. You need a density. And so this is an unstable process. So it's going to be tough, okay? There's not going to, this doesn't, so we haven't, this isn't sufficient to prove equality. However, can we learn an optimal denoiser? Maybe we don't need to actually know what the distribution is. I just need to find a function that behaves like the Bayes estimator on my data. Right? That's all I care about. If all I care about is the MSE, I don't know what the distribution was, but so can I have stability kind of in the MSE? And here it turns out the answer is yes. In a few words, this goes back to some ideas from robust statistics, where we're again going to be using first some factors like, after all, conditional expectation under Gaussian noise can be expressed simply as a function of the distribution of the observations y. All right, so this is the expected value of x, but we never have to compute the distribution of x on the right-hand side to say what it is. So this is a useful relation. And then we again show then that you want to find some plug-in tool here that will work well for all possible x that are close to what you observed. But I'll leave this again as a questions for future research. How well does this work? And to what extent is the min-max similar to the max-min? I think this concludes my talk. And again, so kind of the overall thing was, hopefully I've conveyed to you this, I think, powerful and surprising thing. Undersampling has this effect of adding noise. I showed it to you. I said it holds in a bunch of theoretical cases. And then I've talked a bit about how we can use this fact to design optimal algorithms and know precisely when they will work and when they'll fail. Thank you.
We actually are over time, so I'll take a couple of questions, very quick questions. Any questions? You don't get to ask questions. You ask your questions. Any questions? All right. If not, let's thank us.